and some of them they take up the this industry jobs as well. So feel free to see our departments, our departments instrumentation facilities, lab facilities, and if you have any queries, like you just burst upon anyone and then ask what is going on and what's happening here. So you are welcome to do that. So I hope that you stay here and make your stay pleasure and memorable. So coming back to this program, for what you are here. So this is called Gyan course. As you all know, this is a global initiative of academic networks, which is a great initiative by Ministry of Education now. Earlier it was Ministry of MHRD, to invite globally acknowledged faculty. And you know, it is Oliver Reiger, so who is globally known, and while if you see his CV, I think it will be nicely, you will understand that, okay, why he is here and what you are going to learn in this 4-5 days. So the course, which is organic, like advanced in organic synthesis and catalysis for a sustainable future, will be for 5 days, and it is about 17 lectures and 4 tutorials. If you have seen the course structures, whatever have been plotted to you. And as Sangeeta mentioned, that 4 of the teachers will teach you about this course, which will be on organic synthesis, catalysis, and the synthesis from your photolytic conditions, from electrolytic conditions, and flow chemistry as well. And when you make something, you have to characterize them. So that's why the spectroscopic term is there, which we will learn them, and some computational aspect of this catalysis you will learn. And I hope that this course, at the end of the day, you will enriched by these lectures, and when you go back, you will feel with some like a happiness that we came here to learn something, you have done something. So I would say, like, your stay, make it comfortable and have a wonderful stay and your learning in our campus. So not going into more details about what is Gyan and what is our department, which you will learn few days, I would just call upon our today's speaker, that Professor Oliver Reiger, with a short introduction, because his introduction and CV will be so long. So he did his PhD from University of Hamburg on polycyclic aromatic pi systems, and after that he joined a postdoctoral research with Dr. R. Miller in adjunct professor at the University of Göttingen. Following, he moved to University of Stuttgart in 1996 as an associate professor. And finally, he moved to 1997 to University of Regensburg, where still he is there as a professor, full professor. His research area focused on various aspects like natural product synthesis, amino acids and peptides, catalysis, coordination chemistry. So cannot say that only organic chemistry. And solid phase synthesis, photochemistry and electrochemistry. And if you see, like, he has supervised about more than 70 PhD students, 94 master students and 23 postdocs. So that says that how long his research career is and how he is doing things. He is the recipient of many awards, that Raido Professorship, Tokyo Institute of Technology, then Fellow of Innovative Teaching, then JSPS Research Fellow in 2008, and then Novartis Award for Innovative Organic Synthesis in 2001, Karl Wienerker Fellow, and then Otto Ron Memorial Award in 1994, and DFG Young Investigator Award in 1992, and Fellow of NATO Science Foundations 1990. So he is a member of many scientific societies like German Chemical Society, American Chemical Society, and International Society of Heterocyclic Chemistry. And he is currently a distinguished visiting professor in IIT Indore as well. So I would say, after listening to this CV, which is very small, you understand what you are going to teach, what he is going to teach to you, and what you are going to learn with these 4-5 days. And without further delay, I welcome Professor Oliver Reiser to set up things and go about with his lecture. Thank you all. Thank you.
Okay, I'm not sure what.
Okay. So should we wait until 10 or?
Yeah, maybe 5 minutes more.
Yeah, because the streaming.
The
Yeah.
recording is started.
Yeah.
Maybe we can wait just 5
Okay.
minutes. Or you can talk to the students.
Yeah.
So make yourself, make your students into your class.
Yeah. So then maybe we. Okay, so this is the pen. Okay, so this is the laser pointer. So and then I need to switch. Okay, yes. Okay, and then I need to switch back to the laser pointer, right? Because they will not be able to see. Okay. All right. Good.
Maybe you can use your
Well, if I use the pointer, they will not see it in the streaming. Right? If you use the laser pointer, you can see it here, but it will not be on the computer. So I need to do this here. So here, you see here I have it. And so, as you can see, this will be probably the only lecture you had before where you're encouraged to use your mobile phone. Right? So if you have a mobile phone or tablet, then you are supposed to either download this app or open on the browser, this page, slider.com, and then people use their phones during the lecture, right?
Yeah, that's right.
We do this differently here.
Yeah.
Okay. Yes, I'm not sure if I'm supposed to wait until 10 so that the streaming makes sense. So we can start this, or yeah?
So the streaming will start from here.
It starts already. Okay. Okay. So then, welcome also from my side. Good morning, everyone. My name is Oliver Reiser. I'm from Regensburg, Germany. You will see the map in just a moment. And I'm very happy that you are here and that you are also very brave, right? If you want to sit here through 5 days of many different types of lectures, and I hope you will like it and not to be too exhausted. So So in all my lectures, I would like not just to teach you reactions or talk about and go through many of the reactions. I would also like to do together with you some concepts and some ideas, and which might be valuable for overall doing chemistry and doing chemistry in a sustainable way. We hear so much these days about sustainable chemistry, efficient use of resources, and I would also just like to go over some concepts and some ideas which people advertise and which are behind this. And rather than just teaching the whole time, I would also like to interact a little bit with you, and this is why I encourage you to use your phone. And as you will see during the lecture, there will be questions coming up, and you will be able to answer this with the phone. So let me see if this works. I go this, and so if you are now have opened up your browser or the app, you should be able to enter this number 201294, or you should be also able to screen the QR code. And then you should actually be able to answer this. The good thing for you is I will not know who answered, so it's all anonymous, so you're not getting graded on your answers. You can answer whatever you want, and I actually will not know who is answering what. But let me see if this works. So I hope something will come up there. You should be able to see it, right? I can also check with my phone. And let's see, normally the answer should come up immediately. Yes. All right. See, so this should work this way, and it comes up a little bit scattered. We will later on have this in a little bit more organized way. So it looks like IIT Indoor is the institution you are here, but also, are you all from Indoor? Don't know. See here now lots of names. So you see, this is the way this is supposed to work, and looks like it does quite well. Okay, so the one thing I don't know about you is how much chemistry are you familiar with? Which degree do you already have? And so this would be my next question. Which chemistry degree did you obtain so far? Oh, so some of you already got the PhD. So you will know everything about this course, what is going on, and so... Or they are doing it, yes. But if you read carefully, the question is, which chemistry degree did you obtain so far, not which one are you pursuing? And you can see, so most of the participants we have here are master students, and they're doing a PhD. Okay, that's very good. So, and maybe just very few doing their masters and having obtained a bachelor degree. Okay, so very good. So as you will see is that there will be very different levels in this course. Some things, as I say, general concepts where there's almost little knowledge necessary for the course. But there will be also some more advanced concepts and reactions, and I will try to explain everything as good as possible so that everybody is able to follow. So in this first class, I would just like to talk a little bit about the idea of green chemistry. Right? We hear about this all the time. Even outside of chemists, we talk about green. We have green parties. So the idea of green is very much embedded now in our thinking. But let's talk a little bit about what does this mean for chemistry. And so before I do this, let me just show you very quickly from where I am. So here is the city of Regensburg, and we will come back to this map at some point later. So Regensburg is in the south of Bavaria, south of Germany. Munich, you might heard of, is the city here. Oops. And the university is pretty new. Was founded 1960s, 1970s, and you see our campus here. And the city is located on the river of Danube. That's the largest river we have in Europe, at least in Central Europe. And it has a beautiful old city, old cathedral, very different, I believe, from the type of cities you have here in India. So if you have ever the chance to visit Germany, and I'm sure at a later point in your lifetime this might be the case, Regensburg is a pretty nice city to be in. Okay, so let's talk a little bit about green chemistry in the context of organic synthesis. What does it actually mean, green chemistry? And I could ask you this, right? What are principles of green chemistry? What do you associate when you think about doing a reaction or doing something in the lab? What do you consider to be green and what do you consider to be maybe not green? So maybe you can give me some ideas what you think is green, what would be green chemistry. So also far we have a blank screen here. Atom economy. Okay, that's a good thing. It's something I am going to cover in just a moment, because indeed this was a buzzword which came out around the 1990s by Barry Trost. Barry Trost, a professor of Stanford University, he coined a term, and you will see in a moment what this means. Renewable energy. Okay, so energy is a very important point when you do chemistry, right? And indeed, many of the processes we do these days are very energy intensive, and we will see examples to this. And the question is that a problem or not? And whoever wrote this has written a very important term. If the energy is renewable, then essentially this might not be a big factor in the process which we are doing. Ideally, if the energy would be sunlight, which is coming down on our planet every day anyhow, then it would be maybe even abundant, and then energy would not really matter. Let's see, green solvents. That's a very good term. But the question is, what are green solvents? And we need to talk about this as well, because there are some people who advertising certain green solvents, which I think they are probably not so green as you might think. Very good. Catalysis, absolutely. That's much better than doing things stoichiometric. Waste prevention, okay, less hazardous substrates. You guys know all the buzzwords. And indeed, these type of buzzwords are all were written down in the so-called 12 principles of organic, of green chemistry. And if I count this through, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, looks like we're pretty close to also naming 12 aspects. Yes, so you guys like atom economy, and I think that's a very good point. So there are a number of definitions where people have said what should consist of green chemistry, right? And they say should reduce or even eliminate waste, eliminate hazardous substances, and very important, you don't want just to look at the reaction you're doing in the moment. You look at the lifetime of a reaction and the product, starting from the design, manufacture, but also of the disposal. You might have a very atom economic production of a product, but if it is consistent and you cannot use it. Well, it's working so fine. What's going on now? Then of course it might not be as green as you think. So there are some definitions. I think the most famous ones are these 12 principles of green chemistry, which were put down by the Royal Chemical Society, and there was a very famous article who has said this. And I think many things you have already mentioned. So prevent waste, very important. I think very obvious to everyone. But you will see in a moment that even this is not such an easy way to define, because there might be waste which might be very useful, right? There's different types of waste. And one of the most important reactions we have on this planet, we see in a moment, produces a waste. Without that, we could not live. So that's a critical and also sometimes not so easy definition. Maximize atom economy. That was a project, that was something you guys liked very much. Less hazardous chemical synthesis. This is indeed something, you're too young for this, but when I did my PhD, unfortunately, in the introduction, all these years were disclosed, so you can see that I'm already quite old. When I did my PhD 30 years ago, chemistry was a lot less safe. Okay? And so indeed, designing less hazardous chemical synthesis and safer chemistry and products is something I feel has been a major accomplishment of chemistry and also of organic chemistry over the last, whatever, 30 years, 40 years. Solvents and reaction conditions, safe. Increase energy efficiency, right? Somebody said renewable energy, but also to make processes more energy efficient is very important. The type of resources we would like to use, something I would like to talk quite a bit with you, is the renewable feedstock. Avoid chemical derivatives. That is something, now the mic is gone. Guys, why are you playing with this? It works so fine, and now it's gone. It's not on there. It's okay? It's working? Okay, and so avoid chemical derivatives. That is something we do a lot still in chemistry, like putting on protecting groups and taking off protecting groups. This is all kinds of derivatization, but ideally you would find reactions, and nature is doing this very well, right? Nature is not using any protecting groups, and that is also a very important goal in organic chemistry, right? Catalysis, those stoichiometric reagents. Design for degradation. Once we dispose a product, can we degrade it to either to environmentally harmless products, right? And for this, you need real-time analysis to prevent pollution, something not just when you maybe look at when you dispose your product and then look in the long run, but you need to look at this over the whole process. And then, as I already said, minimize potential for accidents is something I find also very important, has improved a lot. If you look over the history, fortunately, if you look at major chemical accidents, let's say in chemical companies, plants or so, fortunately, there are very little if you consider how much chemistry is being done. And so I believe that it's, again, a major accomplishment that chemical processes has been made safer and safer over the last years. So let's look at some of these things you said, like operational efficiency. And so I'm just showing some ideas in here. So if you look at an industrial process and you would like to run a reaction, what do you think is the least desirable, not the best, but what do you think is careful here, the least desirable temperatures to carry out a reaction? And so I just give you some ideas here. And I can see that you guys have very different ideas about this. And you can also see that you can correct answers and take back answers and all these issues. Okay, so I'm not completely sure, maybe the question, if it was phrased okay. So you guys don't like the high temperature in the as a process. We will see many industrial processes which run at such high temperatures. And in fact, the high temperatures very often are not so much a problem. It's energy intensive, it's no question about this, but it can be handled very well. And very often high temperatures, but then the reaction times become very short, are very efficient, and even from an energy point of view. And so high temperatures, I put down 500 degrees, 200 degrees, 100 degrees. That is typically not so bad if it is run efficiently. Ideally, you would like to see a reaction at room temperature, right? Because that is what we have around. So room temperature in Germany is 20 degrees, room temperature in India is 35 degrees, so not so easy to define this. And but the one thing which is really critical and industry hates and is hardly doing are low temperatures. So 0 degrees might still be okay. You can do with ice cooling or some cryos. Minus 20 degrees might still be okay. But anything you need to go below this becomes difficult, and it becomes energy intensive because you need to make the low temperature. But there are other problems with this. So there are problems with that you start forming ice everywhere, right? If you run a reaction in your lab, you do a reaction at low temperature, you start forming ice everywhere. You condense water into your reaction flask very easily. So low temperatures are much less desirable, minus degrees temperatures, than high temperatures. Okay, so I'm not sure if you're old enough, but you said safer chemistry, less hazardous way. Do you know any type of typical chemistry which is more efficient today than, I think, on your time perspective, probably 10 years ago, my time perspective 30 years ago, which became much better to do? And as I said, there are no answers here, so that's probably because you are too young. You don't know the differences. Okay, so the Wittig reaction, we will talk about the Wittig reaction today in the tutorial. I'm not sure if it has changed. It's still more or less the other thing. So two persons of you mentioned photochemistry. This is something, again, if you are old enough like me, you would completely agree. And we will have a whole day on photochemistry and photocatalysis. Photochemistry is a relatively old technology. It was done in the 60s, it was done in the 70s, but one of the big differences was that it had used these high intensity mercury lamps, which generated a lot of heat. And so when I did a photoreaction in my PhD, which we would do with these high pressure mercury lamp or medium pressure mercury lamps, which generated a lot of heat, we had to make sure that the cooling would work, and we would have to make sure that the cooling would not stop. So for some reason, the water cooling would keep flowing. There's no tube would go, would maybe break, or there would be a water shortage. So if I would like to run a reaction overnight, this would mean I would have to stay in the lab to make sure that everything is okay. I could not dare to go home, because then if something would go wrong with the cooling, this whole thing would probably explode. And so this, and I think this is one of the major driving forces of photochemistry today. Now we have LEDs, which generate a lot less heat, depending on the wattage. It still might generate quite a bit of heat, but we can just shine an LED from the outside of a flask or from some plate we use, and that has become much safer and much easier to operate. And I think this is one of the issues we have now, that chemistry became much more applicable in operationally synthesis. Electrochemistry, electrocatalysis, I'm not so sure. We will talk about this as well for one whole lecture. I think there we have what has made it more easily to operate is that we can now buy kits, the whole reaction setups, which you can just start using. But we would do this 30 years ago in the same way. We just had to build it ourselves. So I'm not completely sure if this was a driving force or if the whole principle of one electron chemistry, which we will discuss in photochemistry but also in electrochemistry, if this really was a driving force. Okay, so let me, in order that we are not going on too things, I need to make sure that we are not running too much over the time. So let's start with the atom economy. This is something you guys like very much. So name a reaction which has little or no waste. This was what people like Barry chose. He started to emphasize this with the term atom economy. But then there was also people like Barry Sharpless, Nobel Prize winner, a twofold Nobel Prize winner, who emphasized the idea that reactions which can be in a way addition type reactions have little or no waste at all. So somebody says the Aldo reaction. It's an interesting question, because in an Aldo reaction, that might be maybe atom economic, because if you add an enolate with an aldehyde, that's a net addition reaction. You need to make the enolate, right? And so for the enolate, we are using base, and very often we are using base in a non-aqueous environment. So typically LDA, right? Lithium diisopropylamide, or maybe even butyl lithium. And so then we are starting massively making lithium salts as waste, probably more than the reactants which we have, right? So addition reactions, cycloadditions, that's a pretty good idea, right? So somebody wrote also the Diels-Alder reaction. That's a typical prototype of a reaction. Hydrogenation of alkenes, that's also very, very important. And Michael addition. So you see already the idea. All types of additions is typically a very good way. I need to see what I need to do if I want to, if I want to use the pen, cannot use it, right? What do I need to do in order to switch back to the pen now? Okay. Okay, now here it is. Okay, then I can do it. It just didn't show up on the slide, right? So you said addition reactions, and if you like the Diels-Alder reaction and so on, if you look from an industrial point of view, indeed the one reaction we are using probably almost, and if you at least talk about catalysis, almost using the most are indeed hydrogenation reactions. So let me see if this works now. So if you have obviously, if you add hydrogen across a double bond and the alkenes, you typically will get somehow from fossil fuels, from oil. But then the other reaction, which is really done on tremendous scale, oh, gee. Okay, so let's see again if I need to switch this. So pen. So the other reaction, which is very related, which is done in industry a lot, is the hydroformylation, right? Addition of hydrogen and carbon monoxide. And this will generate aldehydes, right? And so both of these reactions, the hydrogenation, where you get the alkenes from the fossil fuels, but also in order to make functional molecules out of this, the hydroformylation is a very important reaction. And both of these are catalyzed reactions, right? So typically we can use many precious metals, palladium or not so precious metal, nickel. The hydroformylation is typically done by cobalt or rhodium catalysts, which is been done. And again, we are talking here reactions which are done on million-ton scale. We are not talking small reactions, right? Reactions like the Elsalder reaction, indeed, dream-type reaction, addition reaction, that is, from an industrial point of view, probably a lot less being applied. So now if we look at, so let's look at the concept you guys all liked so much. This is the concept of atom economy being pioneered by Barry Trost in 1991. Barry Trost, still a professor at Stanford University, very impressive CV. If you heard about CVs, I tell you what an impressive CV is. Who of you is already 24 or older in this auditorium? Okay, so some shy. Barry Trost, at the age of 24, became an assistant professor at University of Wisconsin. So he had already finished the PhD. He was so brilliant that he didn't need a postdoc. They made him a professor right away. And I think at the age of 30, he was a full professor and has done, he is now in the middle of the 70s, I believe, has done numerous contributions and has always been up for the Nobel Prize in chemistry. And so he coined the term atom economy. And with atom economy, he was defining this. What is the molecular weight which is in the product compared to the molecular weight in the reactants, right? And so with this type of definition, an addition reaction, like a hydrogenation, is 100% atom economic, because your alkene and your hydrogen, these are your two reactants, everything goes into the product, right? And so you have a percentage of how many reactive atoms remain in the target product. And you can have this, you can calculate this as a single reaction or as a whole, a series of reactions, and you can look at this, right? And so this was his definition. And now let's look at an example, which is not 100%. And so that's the biological photosynthesis, right? And in that biological photosynthesis, you react carbon dioxide with water, and that is done by the sunlight, and you have a catalyst, which is chlorophyll. And with this, you're getting out sugars, and then you get 6 molecules of oxygen. And so if you would look at the from an organic synthesis point of view, if you would look at the product formation, then the sugars here would be your product, right? And if you now calculate the atom economy, then you would have 6 molecules of carbon dioxide, so that's the molecular weight here, 6 molecules of water, and so this gives you the net sum of your starting materials, and then you would have the product, which is here your sugar is 180, and if you divide 180 by 372, you come to an atom economy of 48%. That's not very high, right? And there's waste apparently produced. But look at this, at least, and that's why I said we need to be careful what we define as waste. The waste is oxygen, and this allows us to breathe. Without this waste, we could not live on Earth, right? And so atom economy might be, from the organic synthesis standpoint of view, might be very, very low, but maybe with the byproducts you might form are very useful. And you will see that this is a strategy which is done in industry a lot, and especially in companies, big companies like BASF in Germany, who can do everything, who are not doing just one process, who are doing hundreds of different processes, and very often they are able to do something very useful with what we call waste is being produced. Okay. So there is also the atom economy concept, which was introduced by Barry Trost in 1991. After this, a lot of other factors were defined, because people said, well, maybe atom economy is not the only good measurement we should use. And very importantly, there's something like an E factor, which was introduced. There's something which is called reaction mass efficiency, process mass intensity. I give you a short idea of all of these type of parameters, and then we can look at this. Okay. So we don't need to do this. We have already named a number of reactions with perfect atom economy. So let's skip this. And so again, this is another example for an atom economy. So if you consider like an esterification of this carboxylic acid with methanol, catalyzed by an acid, you form the methyl ester and water. You probably have even done such a reaction in your laboratory. Experiments and lab courses. If you calculate the atom economy, it's actually pretty good, right? It's 87% because this is your product and these are your starting materials, and so you can do it yourself. You find out what it is, and the byproduct is actually pretty benign, right? Because the byproduct is only water. So people pointed out very early that there are limitations to this atom economy type concept. And one of the limitations is you consider only the reactants, like the two things which are being used here, but you're not considering solvents or reagents, right? So we need a reagent here, paratotal sulfonic acid. We have not really said how much we need. Principle, it's a catalyst. We need a solvent, which is probably also pretty good here because the solvent is probably methanol. We are also not considering the stoichiometry. So a reaction might be very atom economic, but you might have to use one of the reagents in a large excess. But that is not considered in the concept of the atom economy, right? And so therefore, it's the reaction yield, if you take into account excess of reagents, that's not really considered. And we already said that if you have so-called waste products, but which are benign or which are even beneficial, this is also not being considered. And so therefore, people have used other metrics. I just give you here a number of reactions which in the concept of Berry-Trost are very atom economic. We already said additions are very good because they are 100% quantitative. Condensations are probably pretty good. We just looked at the esterifications, and there you typically just generate water, so very little waste, small molecule, but also a benign molecule. But then there are other reactions like eliminations, right, where you need stoichiometric bases. They become not very atom economic any longer, and so obviously everybody has seen this. Additions are great. Eliminations, the reversal of this, are typically not very atom economic. Okay, so we had the limitations, and so then people were looking into parameters saying mass efficiency, where they say, well, we look at the mass of the products, and then we look at the mass of the reactants. And the reactants, now in this type of measure, you take into account that you might use an excess of a reagent, right? And so you filter this in, that your total mass here, so this is your product, and then you divide it by the total mass you employed, and here you consider the excess you have also employed, right? So you can see then suddenly the reaction mass efficiency typically is lower if you have to use anything in excess than the atom economy, right? And so there people felt that this is something you need to take into account as well. And just to give you, let me just skip this, and then there's something which is the E factor, and that is probably the most useful. This is probably the most useful type of definition. This came 3 years later. This came from Sheldon, who's one of the really pioneers of green chemistry and who have thought a lot about green chemistry. And he said the E factor is the mass of the total waste to the mass of the product. And now this suddenly considers everything, right? It takes into account all the type of waste you might have. And I give you just here an example, a simple elimination of a Hoffman elimination where you isolate an amine and then do the elimination, and this would be your product. But then you can see this is being done with methyl iodide, which is not really in the product. You need silver oxide as the base to do this, and then you see you form a lot of different types of byproducts. And then if you calculate the E factor, then you see here, which comes out 12.9. This means that for 1 kilogram of product, you're generating 12.9 kilograms of waste. And that is now suddenly a reaction which might be considered more or less atom economic, becomes suddenly a much more problem. You can see that in this example, the solvent is not incorporated in this as well. And if you look at some of the, I go back now, if you look at some of the industrial processes which have been done in industry at a way, this was a process which was done 70 years ago. The synthesis of fluoroglucinol, which was done on 100 tons a year. You can see this is this 1,3,5-trihydroxyphenol. This is a reaction which people started from TNT, trinitrotoluene, which you probably know better as an explosive. And in a 3-step process, which involved heavily oxidation chemistry and substitution chemistry, they've been able to convert this into this phenol. And the yield of that 3-step process is better than 90%. So from a yield point of view, it's fantastic. But from an economic point of view, it's a disaster, because you can see they're using chromium reagents like crazy. And so they were producing around 40 kilograms of chromium-containing waste per kilogram fluoroglucinol. So the E factor would be 40 here. So that's very bad. So although the yield was fantastic, the atom economy and also the E factor simply was a disaster. And here's another example which I think is also pretty much in everybody's mind, that stoichiometric reactions are typically less effective than catalytic reactions. And let's look again at a famous example, and this is the reduction of nitrobenzene to aniline. This is a reaction which is again done on millions of tons, and a company like BASF. I don't know if you know what the A in BASF stands for. Does anyone know? I didn't put this as a question. Does anyone know what the A in BASF is? You all know about BASF because you have BASF in India. There's a big plant in Mumbai, right? The A stands for aniline, this compound here. Because the big process BASF became big in, and actually even a previous company before, was exactly this reaction, the reduction of nitrobenzene to aniline. And from aniline, you could make dyes. And that is how it really started. Like all the dyes, all the color dyes you have in your clothes, this is actually coming back to aniline at some point. And in order to make aniline, you would take benzene and do a nitration to make nitrobenzene. And so the BASF found this company found that process so important that they put the A into its name. The S stands for soda. That's sodium carbonate. This was the other big process they've been making. Okay, and then this is the traditional process, how you would do the reduction. You would do it with iron. That's a pretty great reagent, right? Because we have iron is the most abundant transition metal on the planet. And so they would do the reduction with iron and as a catalyst, and iron salt, iron chloride. And so the iron would reduce the nitro compound to the aniline and itself gets oxidized, right? And you can look at the atom economy. Again, I give you the numbers here and you could calculate this. The atom economy is not very, very high. The yield was great, and of course iron was very inexpensive. You can do this catalytically, and if you do this catalytically, you can use a nickel catalyst, which also is already very good. So it's not palladium or platinum or rhodium. It's also a metal which is quite abundant, not as abundant as iron. You can do hydrogen, And so if you do this reaction, you get aniline, and you have a much better atom economy, because as a byproduct, you're only making water. You see here as a byproduct, you're making iron oxide, rust. The interesting question is, if you compare this, it's not really clear what is better, because you can run this first process at much lower temperature. And you see here, you need 300 degrees. So that's what we talked about earlier, about high temperature, right? High temperature, and you need pressure. That's another factor. If you do a reaction under pressure, it's a safety issue, but industry is very good to do reactions with carbon monoxide or hydrogen under pressure, right? And so here you can see, if you calculate the atom economy, that's much better. You have not really taken into account the energy you need to use in order to do this type of process. Okay, and so then we talked about safety. And that is another thing which I also will talk with you a little bit more later during the course, that reactions became much safer. And that is a pretty good example here, where people have done the reaction in flow, so where you bring the reagents, you introduce them into your reactor. But also, you see, this is the reduction here of nitronaphthalene to aniline. You see what they're doing here is, you have in the one tube, you bring in your nitronaphthalene, but then in the other one, you need hydrogen. But the hydrogen, you're producing in situ. That again makes it much safer. You don't need to bring in your big hydrogen tank and pressure the hydrogen on and all this right away. They're using water here and then electrolysis, and so they're generating always as much of the hydrogen they just need in the moment to do the reduction. And so then this is being in a flow reactor brought together. It is being pumped through a reactor which contains the catalyst. You see here it's palladium on an aluminum oxide support. And then this way you are getting out the product. And so again, this makes this type of chemistry much safer, and you can also run it in a much smaller reactor and just doing a continuously pumping in your reagents into the reactor and then getting it out of the reactor as well. Okay, so we talked about the E factor, and as I said, this is the mass of total waste to mass of product. And it's one of the limitations is it's not considering recycling. And that's of course another important issue, that if you make waste or whatever byproducts, if you can recycle it, that might become very different how you evaluate a process. And today, later in the tutorial this afternoon, I would like to discuss with you a process where you would probably say immediately, we will compare two processes, and you will probably say immediately the one is much better than the other one. But if you look more carefully into this, and especially the idea of recycling, it might be different. It might be a different way. And also solvent recycling is a very important issue, and which might also make you consider things differently. And so when we talked about the green principles in the beginning, some of you said greener solvents. And the question is, what is a green solvent? And I think most of the people you ask, they will say it's water, because we have a lot of water, and it's abundant, and it's non-toxic. We all know we can drink it and so on. But if you have ever done a reaction and tried to recycle water, it's typically a nightmare, right? If you want to distill water out of your reaction mixture, it's not working very well. And nevertheless, that water you use for a reaction is still being contaminated. You would not like to drink the water after you have done the reaction with this, right? You would know that there are contaminations in there. And so redistillation is very difficult, but also burning is very difficult, right? Sometimes you can burn a solvent, use the energy we get out of this. You cannot do this with water, because that's a good thing. It's non-flammable, but on the other hand, it produces indeed waste, contaminated waste, which you also need to, it's very different to upgrade again, right? And so that's what you need to do. And so also the one thing which the E factor also does not really take into account is what you need to do afterwards in the workup, right? You very often need to neutralize a reaction, then you need to do extractions with water or whatever. That's not in there. And the one thing we also discussed already is it's not taking in the energy you need for a process. Okay, so here again there are more ideas on the same reactions on the E factor, and you can see that the E factors can vary quite a bit. If you just look at reagents, that E factor would be this, but then if you take in the solvent, then the E factor goes up quite a bit, and then if you take in the water you use for producing, but also maybe for extracting and workup, then the E factor, you can see, becomes very, very different. So very often people might, depending what you would like to push, and emphasize the reaction and saying it has very little, it has an acceptable E factor if you just look at the reaction. But all things considered, solvent, water you need for extraction and so on, it might be a very different one. I see some people making pictures. This is all okay. You can make as many pictures as you want. But the handouts are available. So all the slides you see here, I'm not sure how Sangeeta is doing. Sangeeta is in charge of the technical issues here. All the handouts are on WhatsApp, or I don't know where you put it. But as I say, I have no problem. You can make as many pictures as you want, but you don't need to, because we are giving you all the handouts. Okay. And so then people have made nice pictures and diagrams for this in order to visualize the different impacts. And that's something which they call this process mass intensity. So the total mass in the process step, where you need everything, solvents and so on, divided by the mass of the product. And then you can make these nice graphs here. And then you can see that very often the most critical issue is the solvent which goes in there. And that's one of the things where you can make a process very often a lot greener if you are able to use little or maybe even no solvent, right? And then the other issue very often is the water you need to do an extraction for your chemistry. And then reactants might be, and other issues also might be a much smaller issue here. Okay, so then the question, how can you increase energy efficiency of a reaction? And that is something I think we have maybe also, I don't know if you have an idea to this or not. We covered some of the issues already. Not sure if something comes up here. So one of the big issues which we are going to talk about is indeed catalysis, right? So that is a way to lower activation barriers and make reactions more energy efficient. And so let's stick with this. This is something which we are going to look at, right? And so here are some more examples, and it's, I think, very obvious that catalytic reactions are much better than stoichiometric reactions. Again, here's the typical Jones reaction you might do in a lab, which oxidizes an alcohol to a ketone, and it makes chromium waste. That's, of course, very bad. So you have a bad E factor and also a bad atom economy because you're making these chromium salts. But then if you do the same thing with a catalyst and oxygen, that's of course the most benign oxidant you can think about, then the atom economy becomes very good, the waste becomes very good. But again, this is something which requires temperature. And so again, and one of the things to make this more energy efficient is to develop better catalysts which can do reactions then at lower temperatures, right? Okay, so we talked about this. Let me just give you an idea today what people think is acceptable for these E factors. So, right, so E factor is the kilogram waste divided by the kilograms of product. And typically, if you start from fossil fuels, oil refining, that is something you do in tons per year, like 1 million to maybe 100 million tons per year. There the E factor obviously you have to be very low, right? And typically they are in the order of less than 0.1 kilograms. So oil cracking, for example, the idea to make from larger hydrocarbons, make smaller hydrocarbons, this is more or less a reaction. Let me see if I get the pen. So typically what we do in oil refining, right? Let me remind you. Okay, I try this again. What we are doing, right? So in oil refining, we typically we have hydrocarbons. So let's take an octane. And then what we do is by applying heat, we can crack this into smaller parts, right? Because under the heat, we start breaking the carbon-carbon bonds. And so once we form such radicals, we will talk a lot about radical chemistry. If this now takes one hydrogen from here to here, then you form a new alkane, and in this case you're forming ethylene, right? This is one of the ways we do the oil refining and making smaller type of hydrocarbons which we can use for chemistry. Again, this has essentially an E factor of close to 0, right? Because there's no waste. And the downside is that the reaction temperatures you need here are again very high, right? It's a very energy intensive process, and in order to do this, but from a waste point of view, it's a very efficient process. And then you can see there are the other things like bulk chemicals, typically things which we produce in larger quantities, but not on this million-ton scale. Their E factors are acceptable in the range of 1 to 5. But think about this. If you have 5 kilograms waste for 1 kilogram product, that is still a lot, right? That is something you would like to have much, much lower. And then fine chemicals, essentially fine chemicals, everything you can buy from Aldrich, more specialized chemicals already. The E factors, you see, the smaller the amount you produce is, the larger the E factors could become acceptable. And if you make drugs, pharmaceuticals, that is something you typically only do on very often even below a ton scale. Then E factors can become very, very high, because now we are talking about very specialized chemistry. But there you can see is that with modern methods and organic synthesis, there might be a lot of improvement possible here. I will want to talk to you today during the tutorial. I would like to discuss with you the vitamin A synthesis. And vitamin A is a compound which probably just every big chemical company has a process for. And I want to discuss with you this afternoon, I want to discuss with you the BASF process, because this is something I believe one can learn a lot, how you can do a process which looks inefficient, which we can become very, very efficient, right? In the vitamin A synthesis, people typically, they needed these type of ketones. If this gets dimerized, this makes the vitamin A, and vitamin A, beta-carotene, is a vitamin we all know and we take as supplements, which is being added to animal food and so on. So that is something which is being done on very large scale. BASF, to give you an idea, is making 3,800 tons a year of this. And you can see this is not just oil refining any longer. This is already pretty sophisticated synthesis. You see here the chemistry of organon. You see how old this is, 1946. Even I was not born at this time, right? So, and you can see what people have done. And if you look through this, we can look at a few steps and just make some general terms how efficient or how green we would think that this type of reactions is. They all start from this, all the syntheses from the company start from this molecule here, iononine, and I show you how this has been done by BASF, and I think that's, again, pretty spectacular how this can be done. But let's say that is our starting material. So the organon synthesis, they start adding of this pre-functionalized starting material, and they're making essentially a grignard. But they're not making the grignard with magnesium. That is what you usually would do. They're making the grignard with zinc. That's already a pretty interesting choice because zinc is very non-toxic and it's also widely available as is magnesium. And it is it's very selective. You see, you have here a reaction where a nucleophile could attack multiple positions, and so they're making the zinc analogous Grignard reagent, and they're adding it to the carbonyl group here. And you can see something else. They're using a solvent you would not use today any longer, right? We all know that benzene is carcinogenic. At that time, people would wash their hands with benzene, like sometimes, again, and I must caution you, sometimes we do this with acetone, right? Now we have in the lab for cleaning labware, we have acetone. In these days, they cleaned the lab gear with benzene. And they thought that is all great. And we think today acetone is great, it is very harmless. And in nail polishers, sometimes you have acetone. You need to be careful with acetone as well, because acetone might not be so toxic, but it is able to carry other substances under your skin. And so again, you all are chemists, we all do chemistry, and we try to have less hazardous compounds, but some of them are hazardous. And this is why we are getting trained as chemists. We need to be able to use hazardous compounds in a responsible way, right? And that starts even with simple things we use every day, like acetone for cleaning glassware, right? So they're using benzene here, clearly. That's something you would not really do any longer. And you can see something else. It was acceptable for them to have a very low yield here. Nevertheless, this went into a multi-ton process here. So clearly, if you would be a process chemist today, this would be the first step you would like to significantly improve, right? Then they do an elimination, acid catalyzed, they use oxalic acid here, and base. And again, look at this, disastrous yield, right? And then they do a addition of methyl lithium. So first of all, methyl lithium is pretty, is again high energy and difficult reagent. They add the methyl lithium to the carboxylic acid. I'm not sure if you know that reaction. You can add methyl lithium to a carboxylic acid to make methyl ketones. But do you know how to do this? I should have put this up as a question. You need to use 3 equivalents at least. So it's not in the scheme here, but that is highly accessed. So you need 3 equivalents of methyl lithium because the first equivalent you need for deprotonation, the carboxylic acid. The second equivalent, you need essentially that the methyl minus then attacks the carbonyl compound. And that's difficult because it's a carboxylate you're attacking. And that, of course, is difficult. I'm also daring to use this here. I was hoping that they would let me use my iPad, and I was not allowed to do this, right? So let me try this again. So if you have a carboxylic acid, and you do methyl lithium, so that's the first step you do. You make the lithium carboxylate, and then more methyl lithium. Is going to add, and that is a difficult process. And then when you quench this, and that is also a very difficult process, if you quench this with water, or in modern terms, you would quench this with TMS chloride, you might want to look up at this reaction, then you would form the methyl ketone here. That's a tricky, very tricky reaction. It requires at least 3 equivalents of a relatively difficult reagent, right? One of the issues, how would you do it maybe today in the lab? You would activate your carboxylic acid to an amide. You see, this was not available at this time. You would generate a such an amide, and now you can use methyl lithium or also a grignard, and you only need 1 equivalent, and you accomplish the same type of transformation. And so that is probably by far the better way to do this. And you can see here that probably oh, now I need to go back. So, but you can see that they nevertheless apparently were able to do this quite well by working this out, right? And then they essentially do the same type of chemistry again because they need to add the same group again here, and you can see that overall the yields they have been able to accomplish here is relatively low, and you can imagine how much waste that has produced at this time, right? And so there are more steps or different types of synthesis from this. Need to make sure that I'm not going over the tea break. This is the reaction I would like to discuss with you guys in the tutorial. This is how BASF is making this, and you can see they start from the same starting material. They also add a grignard, but then the reaction sequence goes differently, and most importantly, they're using a couple of Wittig reactions. And some of you already said Wittig reaction is an atom. We talked about atom economy or reactions. Some of you mentioned also the Wittig reaction. We need to look at the Wittig reaction, and you can see that they're using this in quite some way. They're making the aldehyde, but then they also condense this Wittig reaction with this aldehyde to make actually the beta-carotene in the end. And that is something I would like to have a closer look at this. Let me just show you quickly. Let me see. That's Hoffmann-La Roche, because I don't want to run over the tea break. Look at this. This is how you make this ionanine. That's the BASF process, and I think this is pretty spectacular. How industry is able to do reactions in a really benign way. So they're starting with these isobutane compound here. This comes from the cracking of oil. And then they're using formaldehyde. That again comes from carbon monoxide and hydrogen, which allows you to make this. And then they do a so-called Prince reaction. They do isopropanol. And again, I could try to draw this here. So you see you have the formaldehyde, and then you need an acid to activate this, and then you add the alkene to the aldehyde here. This is a so-called Prince reaction, and you're getting out this isoprene. Fantastic reaction, 100% atom economy, right? So keep always this idea of atom economy in mind from 2 readily available bulk type chemistry, but which you both get from fossil fuels. You get this both from oil in the end. So then they have isopropanol, and then they do an oxidation. And in the lab, you would probably consider chromium oxide. You can do this at room temperature, fantastic, but it makes chromium waste. Now look how they do it here. They do it with oxygen. Oxygen is the most benign oxidant. I could ask you, what is the second benign oxidant? Anyone know what is, if you cannot do it with oxygen, then you would like to do it with, in the list, it's probably hydrogen peroxide, which is the next one, because hydrogen peroxide makes water as a byproduct. And then probably, which is done a lot in industry, the next one is probably chlorine. A lot of reactions are done with chlorine because then it makes chloride as a byproduct, right? And it's essentially sodium chloride very often, right? But look what they do here. So obviously they wanted to use oxygen. They do this on a heterogeneous silver catalyst at very high temperature. Look at this. Here are the 500 degrees, which we talked about earlier. But what they probably do is they have a reactor with a silver catalyst. This just needs to be heated to 500 degrees. And then they pump their isopropanol, they pump it over, and it is at 500 degrees in the contact. But it's not like you cannot think about this like having a flask which you would heat to 500 degrees for a couple of hours, right? That's not how it works. You have your reactor, and then you distill your materials through this reactor on the hot surface. You heat this to this surface gets heated to 500 degrees, but doesn't mean that your whole reaction gets heated to 500 degrees, right? So that is, even from an energy point, is very efficient. So they make this aldehyde of this, oxidation of the alcohol. And then another thing they do is they do an isomerization with palladium, right? Palladium can do hydrogenation if you have hydrogen present, but just palladium alone is able to isomerize double bonds. And you see that they go from a 1,1 di-substituted double bond, they go to a 1,1,2 tri-substituted double bond. The higher the double bond substitution, the more stable is the product. So this has a thermodynamic driving force to go from here to here, and the palladium, just by adding and shifting the hydrogen from here is just able to isomerize this, right? And then they have these two type of chemistry. Look at this; it's still 100% atom economy. Also, this reaction, the oxidation here is oxygen. The oxygen is gone in here, and then they add the alcohol to the aldehyde, and then the resulting hydroxide group gets eliminated. So they're getting this compound here, and this is set up for a Claisen rearrangement. This can do the Claisen rearrangement. Then they're getting out this compound, and because they have this double bond here, this what comes out here. As I say, you have the scripts. You can go through this in more peace, and if you want to look at this again, this can do a cope rearrangement, and that this gives you the citral here, and that is made by these type of compounds, and related compounds are made by BASF on large ton scale. Citral you could have used isolated also from natural resources, but you would need huge amounts of land. That's the next thing, right? Very often we say natural is better. But if we isolate it from a plant, if you want to isolate a compound in ton scale, we need a lot of land in order to build the plants, right? And that is again, you can ask how green this is if you need to use plants for chemistry where you might and land for chemistry where you might want to use the land maybe for food production. And that's again something we need to talk about. Okay, so with this, I think we all deserve a tea break, right? Is a tea break? Okay, very good. And then in the next one, in 15 minutes, then we really start talking a little bit more about catalysis. Okay, thank you.